So Curie was focusing her work on discovering different radioactive elements, and she did discover 2 of them. Ernest Rutherford, who we learned about in Chem 1A, and others were focused on studying the radioactivity itself. What's coming out of these substances? So the nuclei, not just plural nucleus, nuclei of radioactive elements are unstable and they emit or decompose, emitting small pieces of themselves. And they do this to become more stable. So the categories of natural radioactivity include alpha rays, alpha decay, beta decay, gamma ray emission, positron emission, and electron capture. And we'll talk about each of those in a minute. First, we need to review nuclear symbols, which you learned in Chem 1A, but you might not remember. So this is a nuclear symbol. The X represents the chemical symbol. That's the element symbol from the periodic table. On the left, we have a stacked superscript and subscript. The superscript is the mass number, and the subscript is the atomic number. The atomic number, often represented as Z for reasons related to the German language, is the number of protons in the nucleus. So that number is on the periodic table with the element symbol. The mass number is the number of protons and the number of neutrons in the nucleus of that particular atom. So subatomic particles, protons, neutrons, and electrons. The electrons are so light in comparison to protons and neutrons that a lot of times we can just ignore their mass. So here, talking about a mass number, we're looking at the number of massive particles, so protons and neutrons. The number of neutrons is not given on the periodic table, but we can figure that out by taking the mass number and subtracting the atomic number. And I don't know that they did this on purpose, but if you look at these, it's stacked up here, so A minus Z will give you N, the number of neutrons. Most elements have several different isotopes, and isotopes are atoms of the same element that differ in the number of neutrons. They have the same number of protons, same number of electrons, but the number of neutrons is a little bit different. And so we often refer to a particular isotope as a nuclide. We can represent isotopes using the element name or symbol followed by a mass number or using that nuclear symbol. The main subatomic particles can also be represented with nuclear symbols. So here, the proton, P, the mass number is 1 because there's 1 proton in a proton. And the atomic number is 1 because there's 1 proton in 1 proton, right? And this is a lowercase p because it's not phosphorus. A neutron, lowercase n, mass number of 1, atomic number 0. An electron, E, mass number 0, number of protons, -1. We'll see why it's -1 in a little bit. Is that just looking at it? How can you have -1 protons? We'll see what happens. Okay, so alpha decay. Unstable nucleus emits an alpha particle. That alpha particle is 2 protons and 2 neutrons. So we have a little picture of it here. That's the same, it's identical to a helium nucleus, a helium atom without its electrons. So He, 4 and 2, 2 protons, 4 particles, 2 protons, 2 neutrons. So we got this nucleus, and it just spontaneously spits one of these things out. We can write an equation to describe this, and these are called nuclear equations. They have a lot of similarities to regular molecular chemical equations, but there's some slight differences as well. So the sum of the atomic numbers on both sides has to be equal. The sum of the mass numbers also must be equal. So here we have uranium-238 decaying to form thorium-234. It's emitting an alpha particle. So we're looking at the mass number. Here we've got 238, and over here we have 234 plus 4, which equals 38, right? The number of protons, the atomic number is 92. Here we have 90 plus 2. So that's what we're most interested in, is mass number and atomic numbers balancing. What's very weird, very different about nuclear reactions is that elements often change their identities. There's a uranium on this side. There's no uranium on that side because the uranium changed into thorium. And where does the helium come from? Well, the helium came out of the uranium's nucleus. So we're not balancing letters here, we're balancing numbers. Okay, let's write the nuclear equation for the alpha decay of polonium-216. This is the sort of thing that could be on an exam. So we're going to use nuclear symbols. This is one way of describing an isotope of polonium. It's the element symbol followed by the mass number. If we find polonium on the periodic table, where'd you go? What number? 84. Oh, thank you. 84, right? So 216 is not its atomic number. That's the mass number. So we'll start out by writing the symbol for that isotope. So polonium, the 216 was given to us, and the 84 is from finding it on the periodic table. I don't expect you to know the name and symbol of polonium, but you can answer this question without ever knowing its name. Okay, so that's what we're starting with, and that's going to produce something else. Alpha decay. So an alpha particle is going to come out. I'm going to leave a space here because the book always writes the daughter nuclide first and then the particle that's emitted, even though that's not really the way you write the equation. So that's the alpha particle. So all of this comes from the question. Alpha decay tells me this is one of the products. PO216 gives me the information I need to write this out. I need the periodic table to get the 84. So what I'm going to do now is I'm not going to look at the letters, I'm going to look at the numbers. So over here I have 216 for the mass number, and over here I have something plus 4. The math here is not too hard, but use a calculator if you don't trust your mental calculator. Well, what needs to be there so that when I add 4, I get 216? 212. So I'm going to write 212 in here. So that's the mass number. And then the atomic number, I've got 84 on that side, and I have 2 on this side. So what's the missing number? 82. That's not too hard. What element is this? It's number 82. Periodic table says it's lead. PB. Yes? Yes. This is the symbol for an alpha particle. It's not actually a helium atom because it doesn't have any electrons, but that's the symbol, yeah. alpha decay, this is coming out. Any questions? So we're going to learn some things about the characteristics of the different types of radioactive decay. And we're going to use a vehicle analogy. So we're going to talk about semi-trucks, 18-wheelers, and cars, and motorcycles. So alpha radiation is like the 18-wheeler truck, the semi-truck of radioactivity. It's big, okay? It's big. It's the most massive particle emitted. It has high ionizing power. So when a radioactive particle runs into another atom, it can ionize that atom. It can kick electrons off of it and cause it to become an ion. Because this particle is so big, it has high ionizing power. When it runs into something, things happen, right? So this is like the crashing into the wall. But it has the lowest penetrating power. So here we're talking about damage in a collision. Let me write this out. This is with the vehicle analogy. And penetrating power is getting through a traffic jam. So, ionizing power, semi-truck runs into a brick wall. Does it do a lot of damage? Yeah, it might just blast through that brick wall, right? But penetrating power is we're going to look at a traffic jam. Think, downtown New York in rush hour, and you're driving a semi-truck, and it's gridlock. You're going to have a really hard time getting through, right? Because it's like almost impossible for you to change lanes, and everything is congested around you. So that's penetrating power. So ionizing power, ability of radiation to ionize other molecules or atoms. And this is harmful in living organisms because a living organism has all these chemical reactions occurring that are necessary to maintain life. And so if you've got something in here that's damaging some of those molecules, those chemical reactions are not going to occur in the correct way, and the organism could die. Penetrating power is the ability to penetrate matter. So radiation has to get into a cell in order to damage important molecules inside the cell. If it can't get into the cell, it can't do any damage. Alpha particles have low penetrating power because of their big size. They have a hard time getting through a traffic jam because they're so big. So think semi-truck in a traffic jam. Alpha particles can be stopped by something as small as a sheet of paper or your clothing. Even a gap of air can stop alpha particles. So alpha particles are relatively safe outside of your body because they're not going to get into you, right? Your clothing is going to stop it from most of your skin, and even where it does hit your skin, it's not going to cause much trouble. But if you ingest or inhale these particles, now they're inside where all the important things are happening, and they can cause a lot of damage. Any questions? The next one's called beta decay. So Greek letters, alpha, beta, A, B. In beta decay, we have an electron that's being emitted. So how does a nucleus emit an electron? How many electrons are in the nucleus? None. Electrons are outside the nucleus. So what's going on here? what happens is a neutron can turn into a proton and an electron, and that electron gets kicked out. So one neutron can change into a proton plus an electron. The electron leaves. This is a balanced radioactive or nuclear equation. The mass numbers are 1 on both sides, and the atomic numbers are 0 on both sides. So this is why the electron has a -1 atomic number, because when you form an electron, you're forming a proton. It's the nucleus. I'm sorry, the neutron is destroyed. So these are weird things. Don't work too hard to understand how could that happen. I have no idea. But we can write an equation like this for beta decay. So that's a symbol for the beta particle. Beta decay, you've got your initial nuclide, and you write in the type of decay, and then you balance the numbers, right? So atomic number over here, mass number 228, over here 228 plus 0. Whoops. Down here, atomic number 88. Here we've got 89 and -1, add up to 88. So a neutron becomes a proton, and the rest of that is the electron that gets kicked out. Weird, huh? So what's beta radiation like? Well, this is like a 4-door car. Less massive than alpha particles, not as big. You think helium nucleus versus electron, right? Much smaller. Lower ionizing power, but higher penetrating power. So ionizing power, you're thinking about collision. So a car runs into something, it's not going to cause as much damage as a semi-truck, right? And if you think about the traffic jam, a car is going to be able to maneuver through a traffic jam much easier than a semi-truck. So it can get through, it can penetrate the traffic jam. Beta radiation can be stopped by a sheet of metal. Paper's not going to stop it, it'll go right through. Sheet of metal or a thick piece of wood can stop beta decay or beta radiation. So this is more dangerous outside the body than alpha particles are, because they cause more, they penetrate better, right? So they're outside your body and they can get in more easily, but if they're ingested, they're not going to cause as much damage as the alpha particles. And then we have gamma ray emission, and these are electromagnetic rays, radiation, not particles. So it's just energy. So gamma rays are high energy photons. If you remember the electromagnetic spectrum, we had the visible light spectrum in the middle with all the colors, and that's the part we focused on a lot. But then as you go off to the sides, if you go to the right, you get ultraviolet light, which can give you a sunburn, right? And then you get X-rays, or higher energy, and then way at the end is gamma radiation. Very, very high energy. It has no charge, no mass, so it doesn't change the mass number or the atomic number of the element. Gamma rays usually are emitted with another type of radiation. The symbol is the Greek letter gamma, 0, 0. And so it's not going to affect mass number or atomic number. It's just radiation, energy being given off. So it usually comes with another type of radiation. So here we have uranium, and what kind of a particle is this? It's the alpha particle, right? So we have alpha decay and gamma ray emission. We can predict this product, again, by making the mass numbers and atomic numbers balance. 238, got 234 plus 4. This doesn't change anything. 92 over here, 90 plus 2, and that one's a 0. So how do you know that it's even in the equation? The question would have to say that there's gamma emission. There's no other way for you to know that. So gamma rays are like motorbikes or motorcycles. Lowest ionizing power. When they crash into something, they're going to do less damage than a car, much less damage than a semi-truck, right? But penetrating power, getting through a traffic jam, motorbikes are really good at this, right? Because you can drive between the stopped cars and get right through. And that's what gamma rays are like. They can get through lots of things. So what can stop them? Several inches of lead, like really thick lead box, would stop them. Or really thick slabs of concrete. So when they were building bomb shelters, once the nuclear bombs became, real, it's like, okay, your bomb shelter, your fallout shelter, it's got to have really thick concrete walls, because gamma rays are going to go right through the dirt, right? And so you want to stop the radiation. Any questions about gamma rays? Positron emission. This is also a particle. Doesn't have a Greek letter associated with it. A positron is the antiparticle of the electron. Antimatter is real. Matter and antimatter together, and they annihilate each other. I know, it's crazy. Positron is an antiparticle of the electron. If a positron collides with an electron, the two particles annihilate each other, releasing energy in the form of gamma rays. So what we're going to learn in this chapter is nuclear reactions are a place where law of conservation of mass doesn't apply. Law of conservation of energy doesn't apply. But because mass can be turned into energy and vice versa. So in positron emission, a proton gets converted into a neutron and emits a positron. So for the beta emission, a neutron got turned into a proton and emitted an electron. So this is like that. So the proton becomes a neutron and an emitted positron, and we can write the equation like this. So here's our proton, our neutron, and this is a positron. And they usually put a plus symbol in front of the 1, just to show that, no, we really mean plus. It's not that we just forgot the negative for the electron. So positron is positively charged, electron is negatively charged, and so positron has a plus 1. It's not related to the charge, but that's how you can remember it. So atom emits a positron. The atomic number will decrease by 1 because a proton becomes a neutron. So here, phosphorus 30 has 15 protons. When it emits a positron, it's going to lose one of its protons, so this will become 14. The mass number doesn't change, though, because that proton gets turned into a neutron. And then we have the positron. Positrons are the antiparticle of electrons. They are very similar in ionizing power and penetrating power to the beta particles. So we had semi-trucks, and we had cars, and we had motorcycles. Beta particles were which kind of vehicle? The car. So alpha, beta, it's like A, B, right? And then gamma, you're like, what is that? Well, it's the other one is C. So we went from big to small, big semi-truck, car, motorbike. So positrons and beta particles are like the cars, sort of intermediate in their ionizing and penetrating power. Electron capture is where the nucleus gets something, a particle gets absorbed, instead of being emitted. Where does that electron come from? It comes from one of the inner orbitals of its electron cloud. So the particle's absorbed rather than being emitted by the nucleus. The net effect is that a proton gets converted into a neutron. So we just saw how a neutron could become a proton and emit an electron. Proton can become a neutron and emit a positron. So this is the opposite. So one proton plus one electron can make a neutron. That does not happen all the time, right? Because otherwise, atoms would just be like collapsing on themselves and we'd just be left with a whole bunch of neutrons. This only happens in certain circumstances. When we have electron capture, the atomic number decreases by 1. So here, ruthenium-92 plus an electron capture, and we end up with technetium-92. So the atomic number changes, the mass number doesn't change. And because that's absorption rather than emission, there's no talking about penetrating power or ionizing power. Okay, so this is a table in your textbook that summarizes all of these things. What do you need to know? You need to know the names of these types of radiation. You need to know the symbol for these guys. The alpha particle, helium nucleus, beta particle, an electron. Gamma ray is the gamma, and it's got no mass or protons, so it's 0, 0. Positron emission, emitting a positron. Positron is like the opposite of an electron. So its symbol is the same as the electron, except that it's +1 instead of -1. And then electron capture, you're not emitting an electron, you're putting in, you're capturing an electron. You think you can remember those? I think you can. Just got to practice a little bit. Maybe make some flashcards. Think about semi-trucks and cars and motorbikes. And then you should be able to write equations given enough information. Okay? We also should understand relative ionizing power and penetrating power of these different ones. So alpha, this is a semi-truck. This is a car. And this is a motorcycle. What's the positron emission like? It's like the car. Because this is very much like an electron. Very, very similar things. And this one is not emitting anything. So if you remember the car analogy, penetrating power is, can we get through a traffic jam? Who can get through a traffic jam easier? Truck, car, or motorbike? Ionizing power is, if this thing crashes into you, how much damage is it going to do? The truck's going to do more damage. Kate, we're going to practice this one. I'm going to pause and let you start working on it. Write 3 nuclear equations to represent the nuclear decay sequence that begins with the alpha decay of uranium-235. So that's the first one. So let's write the equation for the alpha decay of uranium-235. So the first thing we're going to do is we're going to write the nuclear symbol for uranium-235. So much of that is given to us, uranium-235. We're missing the atomic number, but that's why we have a periodic table. Uranium is number 92. So it's 92 here. That's the reactant, and that's going to decay, and is going to form something. We call that the daughter nuclide. I guess this would be the mother. So I'm going to leave a space there, and then we need the nuclear symbol for an alpha particle, which is what? It's helium, right? Helium, mass number of 4, atomic number of 2. Okay? So then we're looking for some missing numbers here. This side is 235. This side also needs to be 235. So if I put 231 here, 231 plus 4 gives me 235. The math here is really nice and simple. Here I need 92. I have 2, so this one must be 90. And then I find 90 on the periodic table, and that is 3 nuclear equations. So this is the first one. And now we're looking at beta decay of the daughter. So this is the daughter. So now write another equation showing beta decay of thorium-231. Okay, so let's do the second one. We've got thorium-231. It's beta decay. So symbol for beta particle. What's a beta particle? It's an electron, right? So that's E, 0, and -1. The -1 here is not because of the charge, but if the negative charge of an electron helps you remember that the electron has a -1 and the positron has a +1, hey, that's good. Okay, so then we're going to numbers. Oh, well, this one's easy because that one's 0, so this one must be 231 also. And then here, I've got 90, and I need something -1. So this must be 91, right? 91 minus 1 gives me 90. So I look up element number 91, and that's Pa. Any questions about that one? The third one then, we're going to take the daughter, the product of that one, and do another alpha decay. So we write in the alpha particle symbol here, right, and look at our numbers. So 231, something plus 4, so 227. Some days I can do math like that in my head, and other days I can't. It's okay to use your calculator. And then 91, and here we need something plus 2, so that one's going to be 89. The math here is a little bit trickier because it breaks over a 10, and so what is that? That's 89. Doesn't look like a 9. 89 is a C. Any questions? Let's do a couple more. Positron emission of sodium-22, electron capture for chromium-76. Do those yourself, and then we'll go over them. Okay, so let's do these. Positron emission for sodium-22. So we have sodium, and 22 is the mass number, and the element number, atomic number, is 11. Positron emission means that we have a positron coming out. Positron is like an electron, but it's the opposite. It's the antiparticle. So its atomic number is +1, where the electron is -1. So if we look at the mass numbers. This one will have to be 22, and this one will be 10, right? And 10 is neon. Any questions? Electron capture in chromium 70, I'm sorry, krypton 76. Krypton 76. Krypton is element 36. Electron capture. So here we've got an electron, but it's a reactant, not one of the products. This is being captured, not emitted. So then we're going to add these up, get 76. 36 and -1 gives me 35. I think that's bromine. Yeah. Any questions? So there will definitely be questions on the exam over this material that give you a starting nuclide and a type of emission, and you have to write the equation.